Are you kidding me? That's what I had to do?
I'm going to try to refresh it. Hey.
Okay.
All right.
Thank you.
So click the go live button. Okay.
All right, can everyone hear us?
Yeah, is there anyone on the live stream except for me?
Are you kidding me? That's what I had to do.
Okay, a little laggy.
I'm gonna try to refresh it.
Okay. Cool. So I guess you can hear me.
Yeah.
And by you, I mean the people online.
You know what? Before you start, let me just do a quick introduction. Well, thanks everyone for being here and for bearing with us while we try to figure out why our live stream is broken again. But actually, it's not broken. I just didn't click a button. Anyway, so welcome to Mad AI. Thank you so much for being here. Thanks for joining us. And today, I'm really excited that David's going to be here to talk about AI agents, and specifically generative AI agents. And I'm super excited because him and I chatted at last Mad AI, and he said, yeah, it would be interesting giving a talk, and here he is. So without further ado, I'm just going to hand it off, and we can get right into artificial intelligence agents. Thank you so much.
Cool. Thank you very much, Chris. Hi, everyone.
Hello.
I'm David. So I'm a senior engineer at AWS. I make computers and clouds and things. I work on the chatbot team where I build chatbots. And recently I've been messing a lot with building GenAI Agents. I'm not actually going to talk about any of the stuff I have been building at AWS. This is more of a technical introduction to a framework called LangGraph, which is one way you can approach building agents. This is going to be pretty code heavy. So if you get bored, feel free to wander off. The examples will be in GitHub. Just for context, have most of you used LLM APIs previously? Perfect. We use LangChain. Okay, cool. Well, fortunately, I'm going to start with an introduction to some of that. So particularly, I am going to get into agents. Obviously, that's the purpose of the talk. However, a lot of that depends on basically managing interactions with an LLM. So I'm going to go through briefly exactly what that looks like, what state looks like, get into tool calling, and those fundamentals will be really useful for understanding all the agent stuff that we're going to talk about on top of it. So you probably know this, but most LLMs models are exposed through these message-based APIs nowadays. So particularly, rather than just sending a chunk of text, you'll send a list of messages. Each message will have a role. Typically, you'll start with a system message, which tells the model how it should behave, or at least gives hints at how it should behave. And then you typically do an assorting list of user messages, which is typically messages from a human, and assistant messages, or there's different names for this, but are messages back from the LLM. Now, something that people aren't familiar with LLM APIs is it doesn't really manage the conversation for you. Like on every one of these LLM API calls, you give it a list of messages, it'll add another on the end, and to continue that conversation, you have to send them all back. So like in this instance, we're going to start by just sending a human message saying, tell me the start of a knock-knock joke. The LLM will return a message saying the assistant says knock-knock. If I want to continue that, I will then send back the message that they sent me, in this case a knock-knock on here, and then it will return, oh. So the message it sent back, then I will say, add my message at the bottom saying who's there. It will return something hilarious like lettuce. So just to show how to do that in LangChain, as that's going to become very important as we get into this. So I'm going to walk through a few Jupyter notebooks, which just kind of do all this. That's not the right one. So if you're not familiar with LangChain, this is going to look super weird, but hopefully you can get some intuition for what it's actually doing. So basically, I'm going to use what's known as a prompt template, which is basically the ability to create these messages that we're going to send to the LLM. In this case, I'm going to send it this list. The first one is going to be just that system message saying you're an assistant and knows good dad jokes. And then my input message, which is just going to contain a template parameter called, see these curly braces around it, of a variable called input message. We're going to create an instance of the model. In this case, we're just using GPT-4. Most of all the stuff I'm going to show today would work on Claude, the Anthropic model. Those two are pretty well suited for tool calling. All the other stuff that we're going to show off as agents. We can get into other models and how they work, but I'll save that for now. So we have our prompts, we have our model, and then we're going to create a chain, which is just stringing them together. So eventually we can call invoke, saying that the parameter input message is telling me the start of this knock-knock joke. And then that's actually sent that message off to the LLM. It's going to return some, in this case, an AI message. This is a message back from the assistant with the content knock-knock, just what we showed off. Now, to actually start building up this conversation history, we're going to use this thing called a messages placeholder. Basically, that's a way of just dropping a list of messages into that list. Similar to what we just saw, but I'm going to start with an empty list of messages. Define a function that says, send this message. We'll create it as a human message, append it to my list. Invoke that prompt with this message history variable being this list of history. Get a response, and add that on. So again, it's just going to say knock knock. But now when I call send message, it's going to add that human message onto that list of messages, send the whole lot up to the LLM. Say, let us in, it's freezing out here. Ha ha. And that's just all these messages built up on a list. So that's how we manage interactions, just in a single conversation with an LLM. All good? Perfect. Okay. I am sorry I'm going through all this quite quickly. I want to get to showing off agents, which was to on. So the next interesting thing is tool/function calling. I think it's widely known as tool calling now. So this is basically, before these things, the interactions with models were typically all you send a message to it, they will send some text back. Recent models from like GPT 3.5 onwards and recent iterations of Claude have been specially trained to use what they call tools. So this is something where you provide a list of stuff that the model can do, and rather than just giving responses from its training data, it can pick one of the things from this list to run, well, kind of run, to tell you it would like to run. That can happen, and then you give the response back, and the LLM can deal with that. So this is interesting, as now you can actually go off and at runtime, fetch new data, call actions, do other things. So most of these tools, and both of these models I've described, are described using JSON schema. The fun bit about that is that's a very structured way of communicating with these models. Before this, you would literally have to send human text back and forth, which you then, if you want to do anything in a technical manner, you'd have to pass back out and try and get it to produce structured content in a way you could do that. With this ability for them to actually give you a very structured blob, a JSON object matching a JSON schema, you can now leverage this to do all manner of kind of structured interactions with these models. So I'm going to show you some basic uses of tool calling. And then as we get into agents, you're going to see some very creative usages of how we can actually get these models to indicate doing things through these tool calls. And the way these work is very similar to what we just saw in a basic messages API. So when you call this conversations API, or chat completions API, you'll describe a list of tools literally in JSON schema. So this, I'm sure many of you are familiar with this, OpenAPI, JSON schema, Swagger. Like here, I'm going to say there exists a function called getStockPrice. What it does is get the current stock price for a given symbol. It takes a parameter, which is a string called symbol, and it's described as the stock symbol, and you must supply this if you want to call this tool. So these iterations of these models have been specially trained to know how to interact with these structured definitions. I think technically under hood what's happening is they're actually compiling that into something that goes into the system message. But what it can do then is, rather than responding with text, it can respond with saying, I want to call this tool. Like in this example, we're saying, what is the current stock price of Microsoft? Here's some tools. It responds by saying, well, to know that, as I'm a model, it's not on my training data, I'm going to need to call this get stock price tool, supplying the symbol NFFT. And then, notably, the model providers themselves, like OpenAI and whatever, they're not calling the tools themselves. They are responding with that message saying, I'd like you to call this. And then as the application that's integrated with that, you'll do whatever that tool is, and then generate a follow-on message, the same way you would follow on a message as just a human or assistant conversation, saying that we've called. So the assistant asked to call this tool we just described, and then we're going to reply with a tool message rather than a human or assistant message, with a correlation ID between what the model asked for and what we're responding with. And in this case, my application is providing the content, like $460. The model will then process that, go through its usual thing, and like in this example, respond with a written message saying the current price of Microsoft is $460. So just to show off doing that was bare LangChain, as that's going to come up. So what I'm going to be showing off in these examples about building agents is interactions with a stock market API. So I've written a little wrapper around this Alpha Vantage API, which is just a thing that gives a bunch of stock market data. Not very interesting, very useful if you're into this, but yeah. And then what I'm going to do, so here is just a little client I wrote. There's a bunch of methods on it I've added. I've done some caching and things, so it's not crazy. So I can just call latest price MFST, so it's just the usual Python interaction. Now to bring this into LangChain and expose it to a model, I'm going to use some built-in stuff in LangChain to make that easier. So here I'm going to define this other function called getStockPrice. It takes a symbol. Notably, I'm adding a doc string saying look up the latest price of this stock by its symbol. That's what's going to be used for the tool description that's sent to the model. I'm then going to wrap it in this function decorator called tool, which just adds some gumph to allow LangChain to kind of describe it in the calls we make to models and work out how to invoke it. So it's still working the same way. However, it's actually something slightly different than just a function call. Doesn't really matter for the purpose of this. We're going to rebuild a similar conversation. We're going to start with a chat prompt template saying you're an assistant that helps answer questions about the stock market. Here's an input message. I'm going to create a list of tools, in this case just with this get stock price tool. Bind that onto the model. Under the hood, all that's doing is just adding it to a list of metadata that the model will use when it actually invokes that underlying API and build that example API request that I showed. So when I invoke this, the model actually responds with a list of tool calls. In this case, it's a single tool call saying I want to call that get stock price symbol and return Microsoft. I'll skip through all this, but this is just some little utilities to help look up and call the tool. If we were using LangChain normally, we wouldn't have to do this, but to demonstrate it, I'm going to be a bit more low level. So here, we're going to rebuild a prompt, in this case taking a list of messages in this message placeholder, bind some tools, do this little send message loop, where we're going to take a message, create it as a human message, invoke the chain, look at the response. If it has tool calls in its response, then I'm actually going to immediately run that tool, add it to the list of message history, so the next time I invoke that model, down here, it'll use it. So this is just done with a simple if, looking to see if the first response from the model required tool calls, and then actually doing it. So then, in my little example of what's the current share price of Microsoft, it can do that. It'll get the tool call back on its first run. I'll do that call tool and then send the response back, and it'll be able to give me an answer. And then, because I can keep adding messages to that, and it will send the whole history back to the model, I now say, is that more than Google? So I haven't obviously specified more than what, but because it's part of those messages that we've sent to the model, it knows that I mean Microsoft, so it's going to do a call to look up the price of Google, and it can say, yes, the current share price of Microsoft is this, which is more than Google's share price of that. Steve, I can see your question. Steve asked, are there rules for what tools can do and how fast they should respond? Is it allowed that tool to be another thread of an agent messaging? So that's actually where this talk is going. So there aren't really any rules. It is just the model saying in a structured way, I'd like to do this thing you've previously told me you could do. And then if or how your application chooses to respond to that, whether it takes a fraction of a second or a week, it doesn't matter. As long as you're sending back that response, there's no state kept to the model provider around it. So this is very cool. So the model obviously doesn't know what the current price of Microsoft or Google is, but we can get it to use these actions to work out how to work out what the current price is. So let's reset the message history. And now I'm going to ask, what's the share price of Webtoon Entertainment? I have no idea what that company is. Sorry if it's offensive. They're a company that was very recently listed. So any model that was kind of cut off within the past several months will have no idea what the symbol of this company is because it wasn't available online at the point the training data was cut off. So if I try and do that, it's going to fail miserably. And then we'll get into this in a very small way, but this is actually a big problem. I asked it what the share price of this company was, and it made up a symbol to call the tool with. Like, it's like, oh, you asked for Webtoon Entertainment. Good symbol for that would be Webtoon. It's not the right one, but you know. And that failed miserably, as that symbol doesn't exist. So this is where we can start getting into introducing more tools. So here I'm going to introduce another tool called lookup stock symbol, which will just do a search for a company name, return a list of tickers for what could be possible symbols for this. So if I look up Webtoon Entertainment, it's going to return to me and say, well, that symbol is actually WBTN. I'm now going to rebind tools to this model, reset the message history, and ask, what's the current share price of Webtoon Entertainment? Now, the challenge is, in the original loop I wrote, it just did the first model call, saw that there was a tool call, and then ran that tool and did it back. And the challenge here is it's first called one tool to say, what's the stock ticker of this company? I've done that. And then it's responded with another tool call saying, well, now I know the symbol, let's look up the stock price. So my little crude tool executor wasn't complicated enough. In fact, we need to put a while loop in here, which is basically going to iteratively just keep going back to the model until there were no tool calls. So it's basically waiting for a final response to the human until we get there. So this is just a simple, we're going to invoke the model each time. If it returns some tool calls, we're going to run those tool calls and just keep doing it until it stops making tool calls. So now if I run this, cool. So it first looked up the symbol of this tool, and then looked up the stock price of that symbol it found, and then gave me an answer. Is that all kind of making sense so far? Cool. So, the really interesting thing about this is we've just handed over control flow of our application to the LLM. I've asked it an answer. It's gone to my little assistant that's using OpenAI. And then when it returns a tool call, we'll go and run that tool result, get its result, and provide it back to the assistant. And it will, certainly in that while loop, it will keep doing that until it's run out of tool calls. So now it's effectively up to the model whether we're going to reply to the user or we're going to do these tool calls. Well, I mean, it's up to our application. But it's deciding whether it wants to do a tool call or not. So this finally gets us to agents. there's like a gazillion different definitions of what an agent is. This is actually from the LangChain blog. The chap that wrote that wrote a big article on what is an agent. And I really like the definition of it's a system that uses an LLM to decide the control flow of an application. So this basic example of just a continuous tool executor is kind of the most simple one we can do. But we can go a long way from there. Does that make some sense? So there's dozens of agent frameworks and libraries. I've used a couple of them. There's many more that I haven't used. Today I'm going to pick on LangGraph. This is mainly because I started using LangChain early on. When LangGraph came out, I started building agents with that. A lot of the work I do is kind of low-level research things, really messing with what we can do as agents. So it's pretty well suited for that. As we'll get into, I think LangGraph is one of the lower-level ways of building agents. It is very, very, very flexible, but as a result, you need to build on top of a lot of primitives to build stuff. I know for sure, like some of these other frameworks are much higher level where you can just be like, here's this stuff, work it out, which would make for cooler demos, but here we are. So very simply put, and I was explaining this to Chris earlier, so most chains in what you see in like LangGraph and normal LLM interactions can kind of be described as a DAG where they are kind of going through steps. These steps can be conditional, but it is somewhat directed. You start someplace, you typically end up in one or many. What gets really interesting with some of these agent kind of designs is we now have cycles, whether that's going around tools repeatedly, or some of the stuff I'm going to get into more in the end of this is actually going back and forth between agents with different purposes and letting it decide how to progress with doing things in your application. These flows of logic, particularly when they're dictated by models, can be kind of weird and complicated. LangGraph kind of lets you build, unsurprisingly, a graph to describe the flow around your application, and then comes with a bunch of kind of foundational utilities for how you can actually build applications and APIs kind of using that. So what's most interesting is like LangGraph itself doesn't actually do the model interaction. It leaves that to lower levels. Typically, if you're using LangGraph, that will be LangChain. They make that kind of easy. But it really is almost entirely focused on modeling control flow around an agent-based application. So there are a few key components we're going to get into. So you can think of this almost as like a workflow that's moving around a graph. And the way they model this is they have a consistent state object, which you will start at some point. It will make changes to that state. There'll then be routers which decide which edges around the graph to take. When it gets to the next node, it'll update that state. Based on that output, it will then route that around. And those distinctions are very clear. So nodes can update states. Edges just push you around different ones. These edges can be constant. We'll see some diagrams where you describe if you're always going to take a path, it will be solid. If it's conditional, and there are multiple ways of doing this, it'll be dotted. And when I say a lot of this is very low level, they've really focused in an interesting way on trying to deal with like the hardest bits of building these kind of complex agent systems, which isn't immediately obvious when I do all these demos in Jupyter notebooks. So one of the biggest challenges once you start actually building this is when we talk about having a stateful graph, so particularly when you do this thing that they call human in the loop. So basically, say you're going around an agent system where there are many agents, and at some point you want to halt and like ask for a user input. If you're just in a Jupyter notebook, you can just say, cool, run this thing, input this, type something, get a result. If you're running things on an API, you can't do that. You have to persist the state of the graph at every kind of change or superstep, as they call it. So you can save where a user was at the point moving around this graph, stop, do something, and then come back and start your execution where you were in that kind of graph execution. Now that's actually really hard when you have like stateless API servers and you need to persist stuff. So that's a lot of what this checkpointing and human-in-the-loop stuff is about. It has built-in multi-tenancy, which if you're building APIs for this is also very useful. This is the idea that it can deal with multiple separate conversations at the same time. So it has a notion of what they call threading, which is like if you're having a conversation with one customer and a conversation with another customer, there is a very easy way of making sure those are segregated while running through the same workflows. And finally, it has really rich streaming support. So particularly, a lot of the stuff you do with these models, as I'm sure everyone's familiar, they can be kind of slow. They're actually pretty fast nowadays, but as you add more and more model steps into this, doing something overall takes longer. LangGraph supports streaming each step you take through one of these graphs, which I found really useful for like either visualizing it or like in a UI, particularly when building chatbots. You can do incremental updates, where like in my previous examples where I said, what's the stock price of Microsoft? It said, you know, I'm going to look up this thing, I'm going to look up this other thing, I'm going to search for this company. You can actually display that in a UI as it's happening, which makes the kind of perceived latency of interacting with these systems much, much lower. So let's rebuild what we just saw introducing LangGraph for the first time. Again, I'll work through some prerequisites. So I'm just going to use the same stock market API I just used. This is all going to look pretty similar to what we just saw. Again, I'm going to, in LangChain, define a model. I'm going to define a system prompt saying you're an assistant who answers questions about the stock market. As an interesting aside, I'm going to supply the current date, and then down here I'm actually binding that in. So like every time it's run, it always get the latest current date. It's all LangChain stuff, I'll get into it. I'm going to show the most basic way of building a kind of tool in executing agent. You can actually strip this back and use a bunch of pre-built components, but I want to kind of show the primitives in here. So we're going to start by defining our state. Now in this first example, I'm just going to rebuild what we saw, which is just basically a list of messages. So this is the simplest possible state we could have. I'm going to have a state instance. Typically use a type dictionary or some kind of type definition. The reason for this is actually so it can serialize it behind the scenes and stick it in a database if you need to, but I'm not going to get into that. So we're going to define messages as a list of messages. It's using these Python annotated, like type annotation stuff, to attach metadata. In this case, it has the notion of what it calls reducers for each value in your state. This is so when you get to a node, it can just return changes. And then this function you supply here will be how it works out how to apply the changes from that node onto the state when it invoked that node. So it's just an easier way of adding to state as you go around the graph. And then the nodes themselves are typically just simple functions. So I'm going to define my first node, unimaginatively called agent. It's going to take the state, it's just agent state. It's going to invoke that chain, and then it's going to return just that response message. And because we've previously defined this reducer, what it will do is it will get that original state, whack the new message on, we'll have our new state, then it will decide where to go from there. In this little agent system, similar to that picture of a graph I showed earlier, we're just going to flip and flop between two different nodes, the agent itself, which is the one calling the model, and the tool executor node, which is going to take the list of tools that we've seen, run those tools, and then return tool call messages. As for actually constructing the graph itself, this is the kind of builder for the graph. We just say we're going to construct a state graph with this type of state. We're going to add an agent node. We're going to add a tool executor node. We're going to set the entry points. This is where you come in when you're sort of first state. We're going to say start of the agent. So the agent is going to run. It can potentially return tool calls, or it can return a message to the user. So we're going to add a conditional edge from the agent. It's going to look at that and say, If there's tool calls in the return message, then go to the tool executor node. Otherwise, just finish. And this end thing is just a special case end node for when it's reached the end of the graph. So that's a conditional edge. However, from the tool executor, we know we always want to go back to the agent so it can consume the result of that tool. So this is just going to be a static constant edge. Finally, we'll create our check pointer. So this could be a database. So at any point in this, you could actually halt the execution of a graph where you want to ask a user, do you want to do something? That's really commonly used for like if you have sensitive tools, like in my realm, like if you actually have an agent who decides, oh, I wanted to destroy an EC2 instance, you probably want to confirm with a user before you do that. That's kind of a way you can halt it, confirm something, and then jump back in. And it can do that because it can persist all of this in a database. Here, I'm just going to put it in memory as this is a silly demo in a Jupyter notebook. But it's the same idea. And then finally, I'm actually going to create my application from this graph. It uses this compile method, which basically just does a whole bunch of validation on that graph. And we'll create an instance we can run. So now we can actually draw this. It's very small. But yeah, so this is the kind of simplest possible graph we can construct. When I say something, it'll first go to the agent. That'll go to the model. If it wants to execute a tool, it'll go there. If it just returns a normal response, it'll just end and give me an output. And it can go around this tool executor mode as many times as it wants before it reaches there. So now when I run this, I'm going to start by just which has the highest stock price, Apple or Webtoon Entertainment. I'm going to supply a thread ID, which is how we can demonstrate these kind of different threads. It could be different users or whatever, which are entirely isolated and persisted separately. And then we're going to stream the updates from it. So here you can see. Cool. So here I asked it which has the highest stock price, Apple, this Webtoon Entertainment. It first ran some tools to look up the stock symbols. Then it looked up the current price based on the date, returned these prices, and then it finally gave me back a message saying, summarizing that Apple has a higher stock price. I can then continue this conversation. Because I've had the same thread ID in this config, if I was on the other side of an API, I could just run again, only supplying a partial state. So here I'm only supplying the new message I want to add. It runs through that reducer thing I described earlier, so I can just add on new stuff easily without having to supply everything in one go to the graph. So I'm going to say compare that to Google. I'll do some more stuff. Oh, interesting. I tried looking up the term Google, but then found Alphabet, looked up the stock price for those, and there we go. Under the hood, it's actually persisting a whole bunch of stuff about the execution of this graph, which allows it to do this kind of jumping back and forth. We're not going to get into this in any detail, just let's say it's a bunch there. And then if I just actually hop forward to this, we can actually just build all that stuff I just showed in a single function call with this create React agent. So if you just want to build simple agents like I'm going to be discussing, it is pretty easy. Oh, well, I forgot to supply the date, but anyway. So that's a really, really, really basic graph for implementing an agent workflow. So when I first started doing this and I got that working, I was like, great, now I can just keep adding tools and it can do anything. Woo. So why wouldn't you just use a single Uber agent to do everything? So supplying all of these tools works great to a point. However, most current generation models, if you supply more than 20 tools at once, it'll start getting confused and it won't be able to use them as effectively as a smaller list of tools. I'm sure this limit's going to raise over time. Claude 3.5 has claims about supporting 200 tools or more at once. However, that's limited. Like in my case, AWS has 15,000 APIs, so can't supply them all as tools. So you need to do something smarter to work out how can we optimize what we actually call models with, which normally requires a few steps, or different agents, as we'll get to. And then having just this single prompt of like work out what to do, it works surprisingly well nowadays. However, prompt engineering is kind of a discipline that's shown that like if you actually want to get the best performance for a task out of a model, you should kind of very much tailor the interactions that you're having with that model, particularly tuning the system prompts, thinking about the structure of the messages you send to it. That includes thinking about the tools that you provide to the model. So the way you can take advantage of these things is effectively doing this divide and conquer approach to how you break down tasks and how you have agents execute them. So really, you do want to, in most cases, build systems that have a specialized agent for like each distinct task or purpose that you're trying to do, and then kind of string those together through this kind of control flow, workflow type approach to build an overall system. I'm not going to get into RAG much, but that's also a factor in doing this. And the benefits of like doing this breakdown is you can have very high performing, isolated, testable things and then compose larger application functionality for that. I'm focusing in this talk and just talking about what LangGraph is and how you use it. A fascinating other topic to get into is more the theoretical of like how you actually optimize planning agents or supervisor agents. Like how do you build a multi-agent system where it can effectively use many agents at the same time. There's increasingly kind of numerous approaches of how this has been, how you can construct prompts to do this effectively. I've linked a few here. A lot of these boil down to like telling the agent to make a plan, working out how to break that down effectively, going to execute that concurrently, how to like then pull it back together, reflect on how good that plan was or what needs to change to be able to do complicated tasks, a bunch of tools. But I'm not going to get into a lot of that so far. So what are the interesting design decisions that you have to make when building multi-agent systems? By far the hardest is really this state management. So for all the sophistication you can kind of sound like when you describe like, oh, we have an agent doing this and an agent doing this, and this agent tells this agent to do this other thing, and at the end of the day, in most of these cases, you're still just doing calls to models, which are just sets of these human assistant messages. So you kind of have to work out, with these agents, how do you invoke them? How do you get them to do things? How do you get them to pass control between one another? And how do you get to describe the tasks they do in a way that is going to work with this kind of human assistant message-based API? So I'm going to start by showing the simplest approach, where we're going to have a shared conversation history. So imagine it's a bunch of people reading your ChatGPT messages and can type messages themselves, who are particularly good at prompting in ChatGPT, let's say. And then probably the final example I'll do is having entirely separate agents where they actually have conversations between each other. Now, I think someone on chat asked like how interesting can you get with tool interactions? Well, because we have this structured data way of getting a model to tell us what it wants to do, we can use that for helping us understand the control flow that the model would like to take in a way that would be much easier to pass than if we were trying to pass it out of like natural language. So here, I'm going to take the example of imagine you have like 40 tools, distinct things you want to do. It's too many tools just to throw at a simple prompt and a simple agent. So you kind of have to break it down and have specialized agents. And like one's going to be very good at answering questions about like market data in this case, where I've given it a bunch of tools for doing market data stuff. And I've got another agent who's very good at generating charts. Happens to be about market data in this case, which is not a great example, but they're going to be very distinct. And a supervisor agent, when it gets an initial question, is going to decide which agent it's going to ask to fulfill that request. So in LangGraph, one of the easiest ways to do this is just kind of add nodes between these different agents to kind of do these handoffs between different agents where it will manipulate the state in some way to make these handoffs clear. So bunch of code. Most of this is going to be pretty much the same. But where it's going to start getting a bit interesting is that, as I discussed, we can use tools as a structured way to get models to tell us what to do. So here I'm actually going to have, if we go back to this, I'm going to start by constructing these agents, the market data agent and the charting agent. And I need to give them a way to say, when you're in control of the conversation, go back to the supervisor when you're done. And I'm going to do this by giving it a tool that it can invoke, which is very explicitly tells me, or the application author, I now want to switch back to this original agent. So this is just a type definition. So note the tool itself, like there isn't really a tool execution. I'm just giving it a model of like, this is what a tool could look like. And then when it returns that, I'm going to use that as a signal to hand off to the supervisor agent. So I'm going to start by defining my market data agent. So this is just the same thing we've seen previously, a more specialized prompt. And then particularly I'm going to tell it, when you have performed, you're a specialized agent that can effectively use market data tools to find data for a task provided by the supervisor agent or the user. A supervisor agent will delegate to you when it needs to fetch market data. When you have performed your task, use the return to supervisor tool to return control to the supervisor agent. So we're actually telling it how to use these tools to go around control. So we're going to create the usual set of market data tools we've been showing, and then add this return to supervisor call. Similar prompts we've seen previously. And then we're going to define this other tool shape for the supervisor to invoke this market data agent. So we're going to give this to the supervisor, say delegated task to the market. This is a tool for delegating a task to the market data agent. The market data agent can fetch market data using specialized tools for blah, blah, blah. Give it a task for me to perform. Well, I won't go into too much into parallel tool calling or anything. And it's just going to literally, in the tool description, take a string where the supervisor can say, do this thing to the market data agent. So I'm going to do the same thing for this chart agent. It also is going to have a return to supervisor tool to give the control flow back. And this is a tool for the supervisor to invoke the chart agent. And then finally we get to the supervisor. It says, you are the primary agent in the system that can utilize multiple agents to answer questions about companies in the stock market. You're responsible for delegating tasks to the appropriate agent and ensuring the task is completed. These agents refer to you as a supervisor agent. Delegate to these agents by invoking their corresponding tool. When the task is complete or you cannot complete the task, respond to the user. The user is not aware of there being multiple agents and will only interact with you. Do not mention these sub-agents by name to the user. I love these kind of programming by English, right? Just like politely telling it to do stuff. So the only tools the supervisor has is just delegating to one of these two agents. I'm going to run that. Similarly, we're just going to have a very simple state. In this case, they're all going to share the same messages. Now, to make this work, we're going to find all these particular nodes where they're just invoking their chains. These are very simple kind of LangGraph nodes. The bit that's interesting is to make sure that the models don't get confused. Because they're going to see all of the conversation history for all the agents, they're also going to see all the previous tool calls. So like the charting agent's going to see the calls that the market data agent made to the get stock price tool. So when they actually, how are these agents? I'll get to that. So when we do this transfer between agents, we're actually going to inject a tool message. So when the supervisor says, go to the market data agent, I'm actually going to say, you are now this particular agent in a tool message. Reflect on the previous conversation and use your tools to attempt to answer the latest task. If you have completed the task or do not have the right tools to complete the tasks or simply do not know what to do, use the return to supervisor tool to return the control flow to the supervisor agent. Do not mention who you are, just act as a proxy for the supervisor agent. Do a similar thing for returning control where you say you are now the supervisor agent. And that way, when the model is running it, the last tool calls it will see, it will be the transfer to tell it which agent it actually is acting as. I'm going to give it a bunch of nodes here. Interestingly, we're providing some tool nodes for the distinct market data or chart tools, some routers, won't get into that, router between agents, additional edges. So we just get to actually generating it. Hopefully this should look like the example. Yeah, it's a bit lopsided, but so similar to how we, in here, what we're actually looking at is an encoded version of this. But first we go to our supervisor. It then decides whether it's going to delegate to a chart agent or a market data agent, or just respond or finish the flow at the end. Once we get into these agents, they can run their own set of tools. That's what's going around in these loops here. And then when they're done, they can go back to the supervisor. They can decide to go to another agent or finish. Does that make some sense? Now, just quickly, there was a question on chat about how these specialized agents get assigned specific LLMs. So that was really just in each node, I was invoking the model in here, just kind of calling these chains. These could be different models if we wanted to. And in fact, in some of the agent systems I've built, one of the more interesting things of having different agents is the ability to utilize different models. So the most notable thing I've used that for is where I want to do simple things that I can use on a cheap model, like the lower versions of Claude or Claude 2, versus using like Claude Opus, which is like 40 times more expensive than those other models. So you can pick and choose which tasks go to which models, which can be very helpful. Or at least save a bunch of money, which when you're running millions of things is helpful. So I'm going to start here just saying, between Microsoft, Google, and Apple, which company has increased the most in market cap since 2020, then plot that company's market cap on a graph. So for the supervisor to be able to do it, it's going to first have to work out the stock prices of all those different companies, pick the one that increased most in market cap. Oh, that's even a more interesting question. So it's going to have to look at the market capitalization of these companies at the start of 2020 to now, and then from that, work out which one to ask the charting agent to generate a chart for. I've done some fancy code for printing out the responses, so hopefully we can see it working. It's not printing anything. Oh, I didn't print out. I just printed out the final result. Cool. Okay. Yeah, so it first worked out the market capitalization between the start of 2020 and October 2023. Strange. Anyway. Oh, that was probably its training cutoff. I didn't give it the current date. Anyway. And then finally, it worked out that Apple was the one that increased most in market capitalization since 2020. So it then plotted that in a graph and generated this for me. So I didn't show the control flow of tool messages, but what you would have seen if I printed that was delegations to these specialized agents, and they were delegating back to the supervisor once they were done. It did a couple of loops around that before finally returning. So this is a couple of different agents with specialized tools, all kind of showing a message history to come up with an eventual response. Probably getting towards the end, so let's just rush through this. Some of the most interesting multi-agent patterns I've seen is this notion of building in reflection, or a critic, as frequently called, where to drastically improve the quality, particularly of like large amounts of text or stuff that's being written, or even execution plans, you can have one LLM, like prompt for an LLM to generate something, and then another one to critique it with certain rules. Yeah. And then just loop around that however many times, will drastically improve the performance. Another thing this is used for a lot of stuff I built is building in guardrails. So one of the hardest things with some of these LLM-based systems is knowing whether the response is good or bad, particularly when it's in natural language, and historically that's been pretty difficult to work out. What's good at understanding natural language? LLMs. So we can just rub on more LLMs to try and work out if things are good, safe, or whatever. That's pretty pricey, but oh So in this, we're going to very quickly, because it's getting late, I'm going to generate a multi-agent system where we're going to have these things all talking to one another in their own conversations. So they won't have a shared history. So in some respects, it's going to be like separate people all working together as a team to come up with a response. So in this example, I'm going to ask a manager as a customer to generate a report about a company. The manager is useless, doesn't know anything really, he just talks to the customers. So it's going to defer to an analyst, which I've encoded to be particularly good at working out stuff for a particular company. The analyst has access to a bunch of market data tools and things, and I think the graphing stuff. So it will try and answer the request from the manager. When it thinks it's done, it will send it to a separate agent, which will receive that input. It's just like a human message on these LLM calls. And it's got a system prompt to say, I'm looking for something that's very concise, accurate, all the facts have links sourcing them, the grammar's good, basically being an editor. And if it likes that, it will approve it and send it back to the manager, who will then send it back to the customer. If it doesn't, it will send that report back to the analyst for it to generate a better answer with feedback. And because that analyst will just have that single conversation of like, I've generated this, then it will receive a human message. In this case, it's being asked to revise stuff saying, please improve your answer by doing this. So it's very similar to like if ChatGPT gives you an answer you don't like and you say, well, what about this thing, or try harder on this. In this case, we're just using separate prompts and models to try and simulate the same thing. It's not the right example. Anyway, so I've got this collaborative agents. So I'm going to walk through stuff that's very much the same. I'm going to create some market data tools, including the charting and the normal message stuff. So in my previous examples, I've modeled the state as just being a single set of messages. Here, we're actually going to store distinct conversations with the manager, with the analyst, with the editor, and keeping track of the original analyst request. I don't think we're using that. So in this, we're going to start with the manager. You're the manager of a financial services firm who helps customers write with questions about the stock market. You have access to an analyst who can generate charts and write reports. If the analyst tool provides you a report, you can send it directly to the user. So then we start defining tools for the analyst. In this case, we're going to define this tool shape saying, I want to submit this report if generated to approval. I'm going to give it some content of the actual report, and I'm going to supply some comments. So this is particularly useful for like, say it's generated a report, it sends it to the critic editor, and the editor responds with, actually tell me more data about some event. If it doesn't have access to tools to actually work that out, it can actually go straight back to the critic with comments saying, sorry, I can't do that, whatever. So in this analyst chain, we're going to say you're a financial analyst capable of writing reports on the stock market. Only use data you can source from the tools provided. Make sure to look up company names. Here's the current date. And when we bind tools, we're going to take all the market data tools plus our submit for approval. I'm going to skip over some of these LangChain bits. And then these are the tools that I give to the editor. So these are just simple revise, which is going to be a signal for me to say, send this back to the analyst. With a description about what you don't like about it and how they should revise it. Make sure that feedback is concise and actionable. Or they could just approve it and send it for delivery to the customer. You're an editor, financial services firm. Ensure the content the analyst has written is a good answer to good answer for the manager's request, or the analyst has suitably explained why it isn't in comments to you. Keep in mind the analyst only has access to share price and market data for specific dates. We give it that tools. We're going to skip through some of this, so we're running late. So these are the actual nodes. So like in the previous example, I'm going to introduce some nodes between these different model agents to help maintain the state. So when the manager says send to the analyst, it will run through this node. We'll extract the analyst request. And then in this, we're going to simulate the conversation saying the manager has requested that and we send that as a human message to the model. So like this is us having this conversation with this distinct agent. For the send to editor, so this is when the analyst has got the content. It picks out the request that the analyst was given, then picks out the submit for approval request from the analyst, and then we'll start a conversation saying the manager has asked the analyst to do this thing. The analyst has written the content below and provided the following comments. So we're just building up these messages to using these distinct conversations. Send that to the editor. If the editor decides to send it back, let's say you've requested a revision, so that's going to add something to the analyst, and then we tell the editor that we've sent it back. All of this starts seeming a bit complicated now I try and explain it, but just basically ways of managing the workflow back and forth. We construct this graph. Here's some conditional edges. Let's take a look at what it looks like. Okay. So you see, start, message from a customer goes to the manager. It can just generate a response immediately. So if you tell it, ask for a dad joke, it will probably just tell you. If it's a request for a report or something involving stocks, we'll send it to an analyst. The analyst will then start its conversation. It can do stuff with tools in this loop. It can send it to the editor. Editor can then decide to return it to the analyst or send the approved message back to the manager. Easy. So I'm going to say, do this example. Compare Microsoft to NVIDIA each year since 2020. And I've done some printing so we can actually see what's going on. The manager has requested compare the financial performance of the stock price trends from Microsoft and NVIDIA for each year since 2020. No. Invalid value. Well, that's disappointing. Okay, now it's fine. I used to be a distributed systems engineer where everything would be very deterministic. This is the opposite of that. Okay, so we can see it's going back and forth. The analyst is doing a bunch of tool calls to try and assemble all this information. Interestingly, this is doing parallel tool calls. So the model can actually say, in one response, I'd like to run all of these different things. Like here, it's, ooh. So the analyst produced this report. Look at that. It's pretty fancy. And a conclusion. And then the editor returned it to the analyst saying the report is well structured and informative, but it needs to include revenue and key financial metrics, not just for 2024. Additionally, ensure that the data for key financial metrics is accurately sourced. I don't know if it can actually do that, but. So it's now trying to work out a bunch of that information with the tools I provided it. Does look like it's got stuck on it. Yeah. It's worked great yesterday.
So is this a great way to burn through cache?
Yeah, it was pretty good actually. Yeah, no, so I do cache LLM calls, but this is providing a different call ID each time. There is a max threshold on how many times around this graph it can go, so hopefully it will stop soon. All right, I'm going to stop that.
And you might have to sell some of those stocks to pay for the GPU usage on these systems.
GPT-4, particularly the new one's quite a lot cheaper, so I've unexpectedly spent hundreds of dollars, a lot less recently. And while that's writing, I'm going to run this one. Oh, you can just walk through this one. Okay. Yeah. Okay, cool. So to focus more on the share price and market capitalization, get on it. So now the analyst is compiling a bunch more data. Okay, and then I sent this one back. Ah, perfect. That looks great. Yay! The editor approved it and sent the request to the manager, and there's my final report. Cool. Yeah, so that's collaborative agents telling each other what to do, trying to come up with a better outcome before sending this back. Here is a comparative analysis. Blah. Very pretty. We're pretty much at time, or way over. I was going to show some hierarchical multi-agent system. This is where kind of what I've described so far has just been a kind of a single graph that goes back and forth between nodes. We can kind of make that as deep as we like. So in this example, I actually had a complex graph for the company researcher, which itself was doing kind of rather fancy agent things to work out. It's basically searching the web, summarizing news things and whatever. And that'll go back and forth. So like in this example, I did a thing where when I got asked for details of companies for a particular time period, it could get all the headlines for a particular company, but that would be a large number of links, like literally 1,000. So I'd do a clustering thing based on encodings to work out the common topics, and then an agent system would work out how to summarize those, blah, 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 blah. Then the same editor critic system we just demonstrated on top of that. Loads of code. Yeah, and then I had it write a complex report looking, so here I asked, why did the Tesla share price dip, then immediately recover so much between 2022 in December and February 2023? Similar graph system, went and clustered a bunch of news articles, wrote an initial report. Editor complained about this, saying the sources were off, so it regenerated a report. Editor feedback, cite better, lack quantitative data, blah, 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 blah. And then this was the final report. So it's all sourced, summarized from a bunch of news that it's looked up. It was quite fun, but I won't go through that now as we're running quite late. So things I haven't got into, agent architectures are kind of fascinating, particularly some of these Rewoo LLM compiler things, which is basically very advanced planning agents. They're very interesting. Could talk about that for ages. Didn't. Hosting LangGraph as an API. One of the things I thought was very interesting, LangGraph, the company, are like doing a hosted API, so you can basically take these graphs and expose it as a GraphQL endpoint. They hint at, it's interesting reading what they're actually doing, so it hints at some of the really challenging technical problems running these kind of agents as APIs. Particularly a lot of the stuff I build is surfaced through Slack and Microsoft Teams. One of the interesting challenges there is I can't stop people from talking with an agent at the same time, so multiple users can chat in the same thread. So what happens when you're processing one request and then another user comes in the same thread and is like, well, how about this thing? Like, do you stop that first execution? Do you try and patch that request onto it? That's actually really hard. As I mentioned in the picture of logos, there was tons of agent frameworks. Some of them are probably much higher level than what I've shown. Yeah. Anyway, sorry to keep you so long. Thank you.
Let's give it up. Thank you so much. Thank you, David.
All right.
Any questions from the audience? I know that online I asked some questions, but anyone here? Anyone have any questions? Here we go. Hold on one moment.
I noticed that you had a lot of printing out and debugging by standard out. Is that the primary way that we debug in this?
No. So most of the stuff I build is done through Jupyter to like prototype, and then I actually move it into like real Python. I actually use the debugger in the VS Code Jupyter notebooks constantly. Brilliant. The printing stuff's more just to show and demos and what's going on. So it is just Python at the end of the day, so if you have a Python debugger, it'll be fine. Does that help? Or, yeah.
I have a question, and you touched on it during your presentation. Being a systems engineer, you look at things very deterministically,
Yes.
and we have a probabilistic system now.
Right.
And trying to debug this,
Yeah.
how would you go about starting to debug these agents if something goes wrong?
So particularly one of the things LangGraph is good at is this rigorous definition of state that it can persist. It will persist at each step. So you can actually see, you can't necessarily tell why it took an action, but you can understand exactly the inputs and exactly the outputs. So that really helps in telling, like, it's really hard when you build these large systems with many agents, when your input and output is just like a single chat message and a chat message coming back, trying to work out what happened behind the scenes and do all those things is very complicated. Having these step-by-step pictures of how it built it up is very helpful. It's my wife.
Oh.
We'll have to go home soon.
You probably want to know when he's going to be done so he can...
And to cook dinner.
So again, thank you so much. Thanks, David, again for giving this amazing demonstration. I really appreciate, and I know the Mad AI community also appreciates your time and effort in showcasing and how to build these agent systems. So thank you so much.
Oh, we do have one more question online.
Oh,
You want me to read it?
yeah, please.
Oh, no, I got it. Do you recommend any workflow tools to design these agents and generate and deploy? Not really. So I think, as I mentioned at the end, each one of these frameworks seems to be starting on cloud offerings for deploying these, which you can be plenty cynical about that, but you have to make money somehow. I think they actually, in a lot of cases, solve some interesting problems that are worth looking at. I'm not going to recommend any right now. Generate. It's fascinating. As I say, like a lot of these other agent frameworks are much higher level, so it'll be easier building these things with those frameworks than what I necessarily demonstrated. And as for designing them, there's a lot of white papers on agent design and agent architecture and agentic approaches. I suggest reading those. They're pretty well covered nowadays. Yeah, that's about it. Thank you very much.
Thank you.